So a subspace is a particular subset of a vector space of nth dimension, and it must satisfy three conditions. The first being that it must contain the zero vector, the second being that it must be closed under vector addition, and lastly, it must be closed under scalar multiplication. Now these conditions can seem quite random, addition, multiplication, the zero vector, where's the quotient vector, where's the square root vector, and that's perfectly understandable because I was confused about that too. But think back when you were learning about the Cartesian plane, and although you didn't have much self-awareness when you were learning this in primary school, now you understand that the Cartesian plane has so many applications that the best way to understand it is to actually just do the questions. It's the same deal with subspaces. So let's go through an example. So this is a subset you're given, and you're not sure whether it's a subspace or not. You need to run through the three conditions. Now the important thing to note when you're trying to prove if something is a subset or not is to look at the defining condition. That will be your first clue. And since the defining condition states that the addition of the coordinates, or the square of the addition of the coordinates, must be greater than or equal to 1, it is unlikely that this will satisfy all three conditions. A good habit when trying to prove something is a subspace or not is to just write S1 to keep track. So the first thing we need to prove is that, we have the zero vector. So we let x equal to y, and they both equal to 0. So what happens when we do this? Well, 0 squared plus 0 squared is not greater than or equal to 1. Therefore, S is not a subspace. Now, to prove something isn't a subspace, you just need to contradict one of the three conditions. Alright, let's see if this one is a subspace. So the first condition is to check if we have a zero vector. So let all the coordinates equate themselves to 0, and we make sure that the defining condition is satisfied. So 0 minus 0 does in fact equal to 2 times 0. So the zero vector is an element of S. Now the second condition, we need to check if it is closed under vector addition. So we have two vectors because we need to make sure that it is closed under all vector conditions. So we need to come up with two vectors which are an element of our subset. So the most common way to do this is to use the vectors u and v. After you have defined the vectors, the next thing you want to do is put them into the defining condition. Next, you want to add your vectors. So u plus v is equal to u1 plus v1, u2 plus v2, and u3 plus v3. This is tedious, that is true, but once you understand the general basics, you'll be fine. So if this is what u plus v is equal to, then you know what's next, the defining condition. Put brackets around things because the next thing that we're going to do is manipulate this side using our defining conditions from the individual vectors, which, I forgot that, that's important. Make sure that you state that the vectors are an element of your subset. Always put that in. Plus v2. And now, as you can see, this is exactly the same as our vectors. We just need to manipulate it slightly. So u1 minus u2 plus v1 minus v2, which, as you can see, is just our two vectors which we previously stated. So substituting our values here from the manipulated format of adding these two vectors does in fact produce a result equal to the defining condition. So we've just proved that this set is closed under addition. So always make sure to close. Therefore, u plus v is an element of S. Now to check if this subset is a subspace, the last thing we need to do is see if it's closed under scalar multiplication. So we have our vector, u1, u2, as last time, which is an element of S, and we also have a constant, which is an element of all real numbers. Now we write down the defining condition for our vector first, and now we proceed with combining the scalar with the vector. So what do we get when we multiply a vector which is an element of our set with a constant? Let's find out. So we rewrite our vector with the constant, and then the next thing to do is put it into our defining condition. Now of course we don't put 2u3 because we haven't actually proven that is what's going on. We manipulate this and we substitute a condition we know is true into the equation. So we factor k out, which is u1 minus u2, which is exactly as our defining condition. We get k, 2u3. And to put 2 on the outside, you just take it out. And there you go. You have just proven that this set is in fact a subspace. And yeah, that is pretty much all you need to know.